Okay, lecture number 9b, entropy changes and the loss work. So in a previous lecture, we have established if we have got irreversibility in a system, there would be some entropy changes. In today's lecture, we would be relating this entropy changing to one of the concept, and that is called as the lost work. Um, Consider if you are considering a system in contact with a heat reservoir. Remember, like for a reversible process, the entropy change in a system is equal to dq by t when the process is reversible process. So during the any infinitesimal portion, which mean like if we are looking for the quasi equilibrium process, the heat will be transferred between the system and to the one of the reservoir, which is at the temperature T, and that means like the system entropy would be equal to dq by T. Uh, in the same manner, the change in entropy of the reservoir, which is actually at temperature T, would be equal to the opposite of the entropy change in the system. So that means like the total entropy change in a system in a reversible process of the system and surrounding would be equal to zero. So that equation relate or that equation is true for any reversible process when the system and surrounding or the system or reservoir is in equilibrium and there is no entropy change in the system and surrounding. Now the conclusion for a reversible process, no change occur in a total entropy produced. The entropy of the system plus entropy of the surrounding is equal to zero. Now let's have another system and let's have another process, and let's assume like we are going from a process which is at which is at a state A to a state B, and let's say assume like we are going from a state A to B in a process which is actually a reversible process, and we are coming back on the same from B to A, but that is in a reversible. So we are moving from a state A to state B under reversible process, and coming back from B to A in a irreversible. So let's have a look at this kind of a system. So that means like if I'm looking at the work done and heat transfer in this process, so that means like work done would be the equation of the work done would be du would be equal to dq minus dw. So that means like it is true for any process. Mean like if you remember, this was the equation of the first law of thermodynamics, and that is true for the reversible and also the irreversible process. So that means like if we can just write it down, like it is always true for an actual process, whether that actual process the reversible process or that actual process are irreversible process. But for a reversible process, du is equal to tds minus w, which is actually in a reversible. So this equation only and only holds for a reversible, while this equation hold for irreversible and both the reversible. We will actually look at this one as a equation which will hold for a irreversible. So again, for a going from state A to B, let's say assume like I am moving in a irreversible, and that is I would actually use this equation. And if I'm coming back from B to A, I would be using this equation, which would be equation, and that would be for an irreversible. So for a cyclic process, if I'm going from state A to B and then coming back from B to A, so that means like in a both thing, it will be the change in internal energy would be equal to zero, and we can relate this equation. So this side of an equation would be equal to this side of an equation. So if I'm looking at it, so the both of these equation, so that means like Q minus W would be equal to TdS minus work done in a reversible process. So that was my actual or irreversible, and that was my reversible process. So let's rearrange this equation for the terms which we are interested, which is actually entropy change, which is ds. So rearranging this equation, we will get something equation like this. So if you can compare this equation, and that comparison is comparison with the equation of the irreversible. Sorry, equation of the reversible in a process in a reversible system. So that means like ds would be equal to dq by t, which is actually reversible, So comparing this equation to a reversible equation to this equation, you can imagine like there is another term which is added to this, to the entropy change. Now what actually this term is, this is the work which we'll be getting in a reversible process and the work which we actually get in a process. That means like the work which we get in a reversible process is greater than the work which we get in an actual process. So where the work is lost, in other words, where the work is gone. So that means like if I'm looking at the reversible work which is greater than the actual work, and we just say like the reversible work minus actual work, so there is actually the work which is not available, or the work which is obtained less other than or in a other than the in a reversible process. So the actual work is greater than the reversible work. Now the above equation, if I can imagine like if I'm comparing again with this equation, so that means like ds now would not be equal to dq by t, but it will be actually greater than dq by t, somewhere like this. That means like there is another term, if you need to convert into equality, there would be another term which would be added to this equation, and then obviously ds would be equal to something like this. So that means like for a reversible process there is something else which is added to the system and surrounding, which is responsible for the change in entropy. So the actually, if I'm saying like change in entropy in any process, so that will be actually from a transformation between any two state. So that means like it will be greater than dq by t, and that's what actually the second law also say, like ds would be equal to or greater than dq by t. Remember like from the last lecture. So equality when the process was reversible, and greater when the process was irreversible. So this is what actually we have already established over here. So equality would be when we are talking about the reversible process, and greater one would be when we are talking about the irreversible process. Now the difference what we are talking about, and that's what the above equation say, like which is the reversible work minus actual work. Remember the reversible work is greater than the actual work. So the difference work reversible minus work actual represent the work done that could have been obtained but it did not actually. It is referred to the lost work, and it is denoted by this. So that means like if I'm talking about the total entropy change in a system and surrounding, ds would be equal to dq by t plus the portion which is actually lost during the process. This is what we call it as a lost work now. So going back to the same thing, same analogy what we have established over here, like the total entropy change in a system and surrounding would be equal to zero. Now we have said like the entropy change in a system would be something like this, and entropy change in a surrounding from the previous thing, it is something like this. Now adding them both equation, you will be getting like entropy change, total entropy of the system and surrounding is equal to d loss by t. Now that means like if lost work, if there is no lost work, if in a process, if there is like reversible work is equal to actual work, so there is no work lost during the process, so that means like the entropy, the total entropy would be equal to zero. But if the entropy, if the lost work is there, mean like the reversible work is greater than the actual work, so that means like ds would be greater than zero. So we have established like the total entropy change in a system and surrounding is equal to the lost work, and that is the work which is lost during the process going from one state to another state. So the quantity dw lost by t is the entropy generated due to irreversibility. Now, if there is no irreversibility, definitely there would be no lost work. But if there is irreversibility in it, so there would be some loss work. So summarizing this one, work reversible minus work actual represent the difference between the work we actually obtain and the work that would be done during a reversible state change. It is the extra work that would be needed to restore the system to its initial state. Now, if you want to restore to its initial state, we have to supply this lost work to the system. So in that case, it will be restored to the initial state. For a reversible process, I said like if the reversible work is equal to the actual work, so that the lost work will be zero and there will be no entropy change in the system and surround. For irreversible work, as the work reversible is greater than the work actual, so there is entropy generated, and that is entropy generated due to lost work. This one is W reversible minus W is equal to T naught delta as total is the energy that become unavailable for the work during a irreversible process. So let's summarize what we have already studied and already studied during for the second law of thermodynamics and the entropy. So entropy is a thermodynamic property that measures the degree of randomness, disorderedness at the microscopic level. The natural state of the affair is that the entropy of the system of the entropy is produced by the all processes. So that means like for the natural process, entropy is always generated. The macroscopic feature which is associated with entropy production is the loss of ability to do useful work. Energy, if you remember, is the ability to do work, while entropy is the loss of ability to do work. It is the energy which is actually now in a not good form or degraded form, which is in a less useful form. And it is sometimes said that there is a decrease in the availability of energy. It is not the energy destruction, it is the non-availability of energy, which is we call it as the entropy. Entropy is an extensive thermodynamic property. We established that one. In other words, entropy of the complex system is the sum of entropy of all its form. Now, for the second law of thermodynamics, for the first law of thermodynamics, we said like the energy can neither be produced and neither be destroyed. But for the second law of thermodynamics, we would say like the entropy can be produced but never destroyed. Is the second law of thermodynamics. Reversible and irreversible processes. So now we totally understand what are the reversible process and what are the irreversible processes. Um, we for the second law of thermodynamics, we actually established three different kind of a system, or three different kind of processes. One is we call it as a natural process. One we call it as a equilibrium process, or which is not moving at all, and one is called as the unnatural process. So for the second law of thermodynamics, they we established like the process or the system would be either in equilibrium or that will be moved naturally. It means like the entropy would be generated. There it will be impossible for a system, for an isolated system, that it will actually generate, it will actually go into the unnatural phenomena. Again, I'm saying like for the isolated system, if you are actually supplying energy to the system, so obviously there would be process which we can move in a backward direction. But again, I'm saying like that would be on the expense of change in energy. So if it is expense of change in energy, so obviously again we are talking over the entropy. So for the isolated system, the it is impossible to reduce the entropy. If the process occur, entropy is unchanged, or entropy is unchanged by the forward process, then it would be unchanged by the reversible process as well, and the total process is irreversible. So total process is reversible. The key idea of reversible process is that it does not produce any entropy. So for the reversible in a irreversible process, the entropy is not generated, is equal to zero. Entropy is only produced or generated in an irreversible process, and once entropy is generated, actually, you cannot destroy it. So it would be staying there. So for many example in a real system, we have got example of a reversible process and irreversible process. So for example, the frictionless movement, we can regard it as a reversible process. Restrained compression and expansion, a slow compression and a slow expansion. So that means like it would be regarded as a reversible process. Energy transfer as a heat due to infinitesimal temperature, and that means like if the process is so slowly moving, the temperature is not increasing, so that means like we would be talking about the reversible process. Electric current in a zero resistor, no entropy generated, so reversible process. Restrained chemical reaction, mixing of two sample of the same substance at the same state, would be actually call it as a reversible. And obviously if you move in a friction process, unrestrained expansion, mixing of different matters, different composition, different state, spontaneous chemical reaction, that would be actually example of a irreversible processes. I hope you understand both the second law of thermodynamics and the entropy and the associated concept of reversibility and irreversibility with it. And also, I hope you understand the concept of loss work, and it is the loss work which is actually responsible for the change in the entropy and generation of the entropy. Thank you very much. Have a nice time. If you have got any question, please let me know in your classroom and I would be able to answer that one. Thank you very much.